Okay.
Okay, recording is started. So thanks everyone for coming. So today we have, I guess we're continuing the compiler talks or compiler related talks. This one is a bit more on the performance focus. So Fractalyze is a compiler team based in Korea who've been doing a lot of work on making a fast ZK compiler stack using MLIR, just heavily inspired by the approaches we see in AI. And Ryan will tell us all about it. Off to you, Ryan.
Okay, thank you for the introduction and thank you for having me on the stage. Hi, I'm Ryan, a co-founder of Fractalyze. In this session, I'm going to talk about how a ZK compiler can be one of the ways to make code that is provable and both is also fast. And this approach is really proven to be fast. So literally, I named it provably fast. Since this is the verified ZK event track, I view our work through the lens of formal verification. There was a new way of looking at it for me, and honestly, a great chance to figure out where our compiler fits into the picture. Okay, let's get started. Here's how today's talk will go in order. In backgrounds, we're going to show you the current state of ZK in the AI era. In why do we need another compiler, we approach the problem using a compiler stack. In how can we design a ZK domain-specific compiler, we're going to design such a compiler. In does ZK domain-specific compiler help performance? I want to show you a small slice of an optimization case that takes a real chunk of the proving pipeline. And in ZKX ecosystem, we have a lot of stacks, so I really walk you through our compiler stack. And in where are we, we're going to tell you about where we are and what we've achieved, and then we'll wrap it up. So, okay, let me start with these three numbers. First one, 75%. This is the new code at Google that is now written by AI. Sundar Pichai said this on stage at Google Cloud Next, and the exact phrase he used is important. He said, AI generate and approved by engineers. So engineers are still in a loop, that's still happening. But here's the thing. In 2024, the number was 25%. Last year, it was 50%. Now in April 2026, it's 75%. So in 80 months, it's 3 times more. Engineers didn't drop out of the loop. The amount of code coming to them just tripled. Second number, 178%. This is from GitHub October's last year's report. AI native repositories now grew 178% year over year. And in the same time, total PRs grew 29% and total commits almost 1 billion. So it's not just Google, the whole open source is also producing code faster. Third number, 50%. This is from Anthropic's agent activity report. Half of our AI agent activity in the world is software engineering, not customer service, not other things, coding. So what do this number tell you? The speed of coding coming out is much faster than human can check it. That's the first verse I want you to keep in mind, and we'll come back to it in just a few seconds. Okay, so AI is writing code faster. In the security side, or it's getting better? Short answer is no. Let me show you. 2023, the paper that it was Wickfield-Shamir attacks a modern proof system. The authors surveyed open source ZK implementation and found 30 Wickfield-Shamir instances across 12 different proof systems and some production code base bulletproofs, Plonk, Spark implementation were shipping with Wickfield-Shamir flows. 2024, next paper was the last challenge attack on Field-Shamir in KZZ-based SNARKs. Here's the bug. If you drive the batching challenge to or in the protocol, the attacker can pick the later round proof values after seeing the challenge. And once you can do that, you can prove a first statement. And 2025, in January, Farragut posted the SP1 ZK VM has 3 vulnerabilities. 2 in SPM33 serve, 1 in Plonk 3, which SPM depends on. The team patched it as SPM Turbo, and the point I want to make here is this wasn't a contract bug, not a key management bug. This was a scheme level flow in production CKVM that people were really using. 2026, back in March, AutoSec posted a blog card on faithful claims breaking 6 CKVMs. The flaw was the public claim data wasn't bound into the fiat sharing transcript before the challenge was generated. So the attacker picks the challenge first, then serves backward for values that pass. The blog has great example. They construct a proof that states, oh, here is a counterexample to Fermat's last theorem, and the verifier accepts it. So as we just saw, one security bug per year, 4 years in a row, there's no sign it's going to stop. The bug is still ongoing. Same family of mistake, new generation of systems every year. And the real question is, how do we prevent this in the first place? The community's answer is formal verification. We hope to prove in a machine that the protocol actually matches spec, not as a paper review, as a link proof that you can rerun. And formal verification is not a future thing. This is being built right now, this year, by people who are probably in this room. On a proving scheme side, we've got ArcLive, VCV.io, Compoly. On a circuit side, Clean, ZK-Link, Clap, RSK. The whole stack is taking shape. And this is the catch. Formal verification alone is not enough. If we verify spec and then run it on production hardware, and the verified spec still has to get to production. And the path from verified spec to production code is itself another place where things can go wrong. If we don't fix that path, the verification doesn't really actually protect what gets shipped. So the questions opens up in two ways, both natural, both important. The first direction, link production. You have a link proof of the scheme, and you want fast executable code that you can trust matches the proof. Then how do you go from one to the other? The second direction, production to link. You already have fast code running today, and you want to lift it back into a link spec so you can verify what's actually running, not just what was on paper. These are different problems. They have different tools, different communities, but this is the bad of today's talk. We believe they meet in the same place. There's a layer that both directions need, a layer that sits between the link spec on top and the CPU code at the bottom. A layer that doesn't change when the CPU vendor changes and doesn't change when the algorithm gets a new optimization. Before we talk about why we need a compiler, let me ground us first. What is the executable code in ZK we're actually running? These are two stages where real GPU time gets spent. The first one is trace generation. If you're running a ZK VM, this is where execution gets traced, and you're producing the data that the prover is going to use. The second one is proof generation. This is where things like sumcheck, entity, MSM actually run, the math-heavy part. Both of these are written today as executable code. Both have to run fast on hardware, and this is the part that make for today's talk. Both of them start out as something very abstract, close to paper math, then they have to become something that runs fast on CPU. And that journey from abstract to fast is where everything we talked about so far, the spec drift, the verification gap, that's where it all happens. So the next two slides are about how the journey makes the code change shape. And every time the code changes shape, the verification has to keep up. Okay, so Let's see how code can change shapes. First, because of hardware, imagine we want to simplify the sum of all the elements in an array. In Rust on CPU, you write a one-liner that sums the iterator, like the first snippet on a slide. The compiler does its thing. You get a sequential loop on a CPU, and it's fine. But for performance, we decide to accelerate this on hardware. Let's say we go to CUDA. Now what you need is a CUDA kernel. That's the second snippet on a slide. And to actually make it fast on an NVIDIA CPU, now you have to think about memory management, host device transfer, thread layout, tiling, all of it. Performance got faster, but the code had to change. Same logic, sum a bunch of numbers, completely different shape. And that's just CPU to CPU. There are at least 5 dimensions where the code has to change. First, CPU to CPU is this one. Upgrading within the same vendor, like Hopper to Blackwire, also change things because the new architecture has different instruction, different warp size, different memory hierarchy. Going to a different CPU vendor, NVIDIA to AMD, that's whole different rewrite. Going to non-CPU accelerators, FPGAs, DPUs, custom ASICs, another rewrite, and multi-CPU scaling, synchronization, sharding, another set of decisions. For a simple sum, this is annoying. For a Montgomery multiplication, an entity, an MSM, this is a lot of rewriting. And every rewrite is a place where the link proof you run on a spec doesn't directly apply to executable code anymore. The code has changed shape. Verification has to chase it. Now, hardware is not the only thing that makes code change shape. Algorithm optimization do the same. Let me give you an example from trace generation. Let's say you're reading a trace, and at some point, you need to encode a value as feed element. You want it in Montgomery form because that's what the rest of the prover expects. The generic way to do that is just calling the feed constructor on your 32-bit value. That's the first snippet on a slide. Under the hood, it does Montgomery multiplication. Circuits have a pattern where you often know that value is just a Boolean, just 0 or 1. And when you know that, you don't need the Montgomery multiplication arrow. You can replace it with a chip select. If the bit is set, you get the feed element 1. If not, you get 0. That's the second snippet of the slide. No math, maybe 20x faster. Here's the thing. At the paper level, both versions are the same. Paper just says encode this value as a feed element. That's it. But because you know something about the input that is a Boolean, your code can specialize. And once you specialize, the code looks completely different. And this is just one example. The general pattern shows 2 categories. Input characteristics. If you know the input is bounded, or Boolean, or sparse, you can specialize. Computational acceleration, the MSM algorithm, the entity algorithm, soundcheck. Every year, somebody publish a faster version, and we end up rewriting again. So again, the code keeps changing its shape, and again, every change makes the link proof on a spec drift away from the executable. Verification has to chase it. Okay, we have seen hardware makes code change shape. Algorithms make code change shape. Every change is a new piece of executable code, which means new link proof you have to write to verify. The next change comes and you write another proof and then another. This is the challenge. We start to create proof synchronization. The proof and the code keep drifting apart and you're stuck running between them, trying to keep them aligned. If you do this by hand, the loop never ends. Every time the hardware vendor changes, every time someone publishes a new MSM algorithm, every time you tune the Boolean specialization, the proof has to chase the code. There's a way out, and honestly, this is the whole battle of today's talk. You put a compiler in the middle, the compiler takes the executable code and pins it to verifiable form, and the compiler takes the verifiable form and generates the production code automatically. And what does that buy you? The link proof now lives on a verifiable form, not on a executable code, not on a hardware. The form doesn't change when the CPU vendor changes. The form doesn't change when the MSM gets a new algorithm. The form is the invariance point between spec and execution. That's how you break the synchronization loop, and that's why we need a compiler. You might be thinking, okay, yeah, but compilers already exist. Why do we need another one? I think there are two reasons. First, general purpose compilers doesn't know the ZK domain. ROC and Clang are CPU centric, and VCC is CPU specific. They're amazing at hardware lowering, but their whole job ends there. They don't know anything about CK math. They treat a Montgomery multiplication the same as any other integer multiplication. They don't see, oh, this is MSM can be decomposed into smaller MSMs because of the algebra. That's invisible to them. Second, domain-specific compiler exists, but for the wrong domain. X-ray and Apache TVM actually know domain semantics. That's their whole thing. X-ray understands mapping, algebra structure, broadcasting, fusion, TVM, the same. But the domain they understand is machine learning, matrix multiplication, convolution, activation function, not the CK domain, not Montgomery, not MSM Pippenger decomposition, not sum check, round structure. So you have two existing categories, general purpose compilers, they don't see any domain math, ML compilers that see the wrong domain, and the intersection in compiler that sees CK domain math is empty, and that's our set. Okay, so let's talk about trust. What you actually have to believe for a verified system to mean anything, axis number one is the proof. Lean verifies the math, but for Lean's proof to mean anything, you have to trust Lean itself. Axis number two, translation. This is where the compiler sits. And in our setup, this axis actually has two layers. The bottom layer is LVM and MLIR, general purpose compiler infrastructures that's been around for decades, audited heavily, mature, we rely on it. The top layer is the CK domain-specific compiler, our piece, the new trust assumption we're asking for, and in exchange, Lean verified specs become directly visible to production code. Axis number three, execution. The hardware vendor for the GPU to actually do what its instructions say, you have to trust the vendor, NVIDIA, AMD, whoever, not our layer. So we are adding one trust assumption, the ZK compiler, and what it buys is the connection between a Lean spec and production code. That's the deal, and one assumption, two layers connected, and the rest of the trust unchanged. All right, so now let's talk about how we actually design such a compiler. First principle, everything is a tensor. What I mean is, where you look at CK math at the level the compiler cares about, almost everything is a polynomial. And a polynomial, whether you store it in a coefficient form or evaluation form, is just a 1D tensor. And once polynomials are in tensor form, the operation look exactly like NumPy. Constraint evaluations, something like A times B minus O across the whole trace is a pointwise tensor operation. A sum check round is a tensor contraction. So when you write P1 plus P2, it's just pencil addition, a simple graph node. The compiler can reason about it the way ML compilers reason about ML math. Once everything is a tensor, the next step is to build a graph out of them. Those are opicals. Edges are tensors flowing between them. So every data dependency is explicit in a graph. Parallel scheduling become obvious because the data flow tells you what depends on what. Now, here's the interesting part. We keep this opical set as small as possible. Most CK math gets decomposed down into small primitive set. And there are two reasons we do this. One, it makes hardware mapping straightforward. The smaller the OP set, the easier op lowers the actual GPU instructions. Two, it makes optimization predictable. The compiler's search space for example, fusion stays small. Once you have the graph, then the compiler walks it down through multiple levels. At the top, you have a high-level graph. Tensor adds, tensor multiplies that level. Like you see on a slide, add 2x and y operands to plus operations working over tensor of 100 elements. The compiler does two transformations here. First, fusion. These adds, 2adds are element-wise operations. Each output element only depends on the corresponding input element, no cross-element dependencies. So the 2adds collapse into one fused operation and one pass over the data, no intermediate spilling to VRAM, global memory. Second, algebraic simplification. Once it's fused, the compiler sees x plus x and notice that, oh, it's just a 2 times x. Pure operations, simpler forms, so he rewrites it to x double plus y. Each step is semantic preserving, same output, less code. At the bottom, you end up with optimized PTX. Okay, let's talk about the last design choice, composability. The modern SNARK paradigm is PCS plus IUP. A new proving scheme is essentially split rounds. Each round commits, then a challenge gets derived, then the next round responds. So in George, this is our new product. We've been designing the round concept. It serves as the building block. What's inside the round is it carries a transcript with two primitives, observe and sample. When you have a message to observe, and if it's too long, like a polynomial, the round calls commit first, then observe the commitment. If it's a short one, just a few bit elements, it observes directly. When you need a challenge, you squeeze. That's the whole round API. And then you're gonna chain rounds together to build a model star, one round per protocol step in order. And the design is coming from PyTorch and Flux. PyTorch made deep learning composable by treating layers as building blocks, and Flux does the same on the JOC side with the functional modules. So you can think of a round like a layer and a proof chain, and then the sequential API, same play, but a different domain. Okay, let's check whether all this actually helps performance. Modern SNARKs being deployed in production right now are subject-based, Aspen Hypercube, OpenVM, GISC. So if you can make subject faster, you're helping basically every prover that ships today. Now, subject is broad and there's a lot you can do with it. And we actually have a story for optimizing subject end-to-end by putting it into verifiable form. We wrap it in something called composite.co, and the compiler can reason about it as one unit, but that's a talk on its own. So I'm gonna skip it today, but what I want to focus on instead is just a piece of proof generation. that takes the longest. When you profile SPN hypercube, you can find that about 70% of the whole proof generation is taken by zero check. And when you open up the zero check, it's essentially one thing, constraint evaluation. You evaluate the constant polynomials across the trace. So today, just briefly, I want to show you what the compile level optimization on this zero check looks like, and what's slow inside constraints evaluation, and what changed when the compiler does it right. Here's what's happening today in production. In many ZK VMs, the way constraint evaluation actually runs is basically a runtime interpreter on a GPU. You have a program, a list of math instructions. The counter reads each instruction, switches on an opcode, applies the operation, writes the result somewhere. Looks like a tiny CPU running on a CPU. The problem is like there are two bottlenecks. One is dynamic indexing. The counter keeps the expression buffer, and which slot it reads or writes only gets decided at runtime. Because the slot index comes from the instruction itself, the compiler can pin those values to registers, so everything speeds to slow VRAM. The second is VM overhead, because every iteration fetches instruction, decodes it, branches. The math unit rarely has time to do math. Here's the insight. The 70% of bottleneck is math, is the VM interpreter. The math itself on CPU register will be very fast. The problem is the math never gets to run on registers because the interpreter shapes get in the way. So if we want this to be fast, we have to take the interpreter out. That's what we do. We take the entire interpreter out, and compile time, we already know which circuit we are proving. We know exactly which constraint evaluation need to happen, in what order. So instead of running a VM at runtime that we read the program every iteration, we just unload the whole thing. The interpreter loop is gone. The opcode decode, the switch gone. The body becomes direct math and load the value into register R0, multiply with that one to get R1, accumulate. And for most chips, it's straight line, and heavier operations like elliptic curve works to carry their own internal loop because the multiplication count is too big to fully unload without exploding register pressures. But those loops are doing real math, not interpreter bookkeeping. That's the difference that matters. The effect. Number one, most intermediate values pin to CPU registers, very little VRAM access for the computation itself. Number two is almost no branching for the common chips. The optical switch is gone and the CPU math pipeline stay full, the math unit saturated. And this is what the compiler unlocks, and the interpreter version exists today. Because writing custom counter for every circuit by hand is impossible, the compiler does it for you per circuit at compile time, no VM. Okay, so that was one concrete piece of what the compiler unlocks. Now let me zoom out to the whole stack that makes that a lot more possible and the ZKX ecosystem. And I promise this will be brief at high level. And the flow looks like this. You write your scheme in Python using a library we call George. And George is the ZK-aware building block library. And JAX traces it down to JAX PR, which then lowers to stable HO. The ML compiler IR we extend for ZK. From stable HO, we hit our compiler ZKX, which produces an HRO graph optimized and lowers to prime IR, our MLI direct for ZK, and this prime IR is lowered to binary. And running underneath all of this is ZKD types, our shared type system. It keeps Baby Bear, Goldilocks, BN254 consistent across every layer. That's the whole pipeline, 6 layers, each one focused on specific job. Let me walk through the pieces. Oh, okay, let's start at the top of the stack. And this is George. The way to think about George is it's PyTorch, but for ZK. In PyTorch, you stack layers, and the framework take care of running them on a CPU. In George, you stack rounds, and we take care of running those rounds on a CPU. A proving scheme is just a list of rounds, and here's what that looks like. And this one gives you two things. One is composability. Now you can build pretty much any proving scheme just by composing rounds. If you want a different lookup argument, swap around, and if you want to add a permutation argument, add a round. The scheme is the list. And performance. And the round in this chain doesn't bounce back to the host between launches. And so the whole chain gets captured as CUDA graph. The prover runs end-to-end on a GPU without host intervention. So yeah, that's why composable and fast. So how does this Python actually become a CUDA graph? That's the next layer, JAX, and does the tracing. The user writes George, and JAX captures it as a typed IR. And before deep diving or briefly introducing a JAX, let me zoom in one level. The last slide shows you George at the proof chain level, rounds composed into a scheme, but inside each round, there are primitives, commitment, transcript, force, and let me show you what one of these primitives look like. When you see on a slide is a market commit, about 10 lines of Python, market treat the commit, takes a matrix and returns a digest, and the intermediate layer digest inside, it just recursively hashes pairs, vmap over the leaves and the vmap over the pairs, having the layer count each round until one element's left. That's the whole commitment. And now here's the key thing. The Python code right here is what actually runs on a CPU. There's no separate optimized kernel, settings, somewhere else, no hand tune, CUDA for. The function gets wrapped in what it calls fused region with a marker, market commit marker, and the compiler treats the whole tree built as a one unit. So at the compile level, the market commit collapses into one fused GPU operation. And at the auditor level, or from the perspective of auditor, it's just the 10 lines of a clean Python that any verification engineer can read and check against the market commit spec. That's what I mean by verifiable form. And the production code and the auditor form are two different artifacts. They are the same code. And now let's see how does the Python becomes a CPU kernel trick actually works. And that's the layers below George. And we call this is a George, JAX. And so how does JAX fit in? The user writes Python that look like NumPy. You import a field type, say a baby bear month from our extensions, build arrays out of it, decorate the function with @JAX.zip, like you see in the example here. And JAX traces through the function and produces a type data flow graph internally, a JAX PR, where every node is a primitive operation and every edge is carry shape and D types. And that JAX PR is the contract. Once JAX has it, the function shape is fixed statically. No Python anymore, just the graph of a typed operation on typed arrays. And the win is that the user writes Python, the compiler gets a clean typed IR, no DSL, no separate front-end language, pure Python. And the two pieces JAX needs are the typed array model. That's where the ZK D types comes in next slide, and the lowering target, JAX, lowers the JAX PR to stable HO, this slides after. And so ZK types is what makes JAX3 work. It's a standalone library, extend NumPy's D-type system with the ZK free types. We treat Baby Bear, Goldilocks, BN254 as a first-class NumPy D-types, just like Flow32 or Int64, but with a modular arithmetic baked into the D-type, inspired by ML types, the library that gave NumPy types like bflow16 for machine learning. And you can see what this looks like in the example on the slide. You add two arrays, and the result wraps modularly a negative input, an input close to the fit modulus. Both get reduced into the right fit element. No manual reduction, no custom multiplication, just adding. And this is the shared vocabulary across the whole stack. JAX uses in JAX-BR, stable ratio uses it on tensor D types, ZKX uses it inside the graph, MLIR uses it at the dialog level, one D type every layer. So unlike the other libraries, ZKD types doesn't lower into the next thing. It sits underneath all of them. And because it's standalone, anyone outside our complete compiler can still use it too. Now back to the top-down flow. JAX hands its JAX-BR off to stable ACO in describing the next slide. And stable ACO is the IR we pick to extend. It's X-Array's existing IR, the one that already lowers PyTorch and JAX program onto GPUs every day. Why stable ratio? Because it already does most of what we need. Tensor operations, fusion, multi-target lowering, already there. We don't have to reinvent any of it. We just teach about ZK. And there's two things we add. First, we attach our ZKD type to the tensor element type. So the same stable HO.add operation now means add two arrays of field elements instead of add two arrays of Flow32. You can see it in the snippet on the slide. Stable HO.add on tensor 3 by Baby Bearmont. And second, we add a small set of ZK-specific ops and few composing markers, and these keep round boundaries visible to the lowering passes. And by extending instead of forking, we get the entire X-ray fusion ecosystem for free, and the general purpose passes still run, only the ZK-specific layer is new. That extended stable HO is what gets handed off the ZKX. I'll compare in the next slide. And ZKX is the extra compiler, and stable ratio comes in, and optimized machine code goes out. In the middle, it builds an HLO graph. You can see a tiny fragment of one on this slide with a baby bear bone appearance, and then runs ZK-aware passes on top of the standard X-ray passes. And the ZK-aware passes are the pieces we couldn't get from X-ray, round level fusion. So round lowers to one replayable CPU unit, like we promised in the design. And Montgomery ring arithmetic fusion, custom corners for hot path like constraint evaluation. And here's the trick: we don't rewrite X-ray, we extend it, and the general purpose passes that X-ray already has, operator fusion, layouts, scheduling still run. We just add the secret domain once on top. And the ML compiler community spent 10 years building this kind of structure for ML. We take the work, ZK-fied, apply to ZK workloads, and after all of these passes, the graph is ready for low-level code generation, and ZKX hands it off to PrimeIR, our MLIR dialect for emission. And lastly, PrimeIR is the bottom layer, and it's a MLIR dialect, actually 3 dialects in layers. At the top, there are elliptic curve dialect, which covers points on curve, scalar multiplication, that level of abstraction. Below that field, prime field, binary field, extension field operation. This is what you see in the snippet on the slide. With the n on a tensor of baby mode elements. Below that, we have modal width, row modular integer arithmetic, limb by limb, and the level where Montgomery actually happens. And each layer lowers down to the next. Elliptic curve goes to field, field to moderate, moderate, eventually Erwin IR and Erwin IR to PTX or Erwin CPU backends, and then in the end, it became binary. Okay, and where are we today? So we have a working gross-16 prover on top of our compiler stack on an RTX 5090 on an SP1 gross-16 circuit. Our prover does it in 2.18 seconds. SNARK, which is Go and tune. The production reference takes 4.9 seconds, so we are about 2.2 times faster. And I want to be careful here. This is not a main point of talk. Performance is a byproduct. The point is that the speed comes while keeping the spec abstraction. The Python code that runs this gross-16 prover looks like math, not like CUDA. And on top of that, we have two proof of concepts running. One is circum to LZK, LZK to stable ACO. This is the trace generation pipeline, direction A, former spec going down to GPU. The other is George to JAX PR and JAX PR to stable ACO. This is the proof generation pipeline. And the starting point we use for is SPN hypercube level workloads. And both are working today, but it's not production ready, not finished, but the paths are real. And one last thing before we wrap up is the roadmap. Let me zoom back out to the front end layer for a moment. And the front end is where the verification engineer and the performance engineer actually meet. And there are two ways the meeting happens. The first way is George as the source. You write your scheme in George, that's Python, and the same George goes in two directions down through JAX, stable HO, CKX, primary into GPU binary, and up into a lean spec for verification. The Python front end gives us the flexibility to do both from one piece of code. The second way is a lean as source. You start with a lean spec, the verified artifact, and then lower it down. Verified ZKVM already had a ROS extraction path through HAX and ArcLib today. We see a natural next step here, lower lean specs directly into stable HY and skip ROS altogether. That's not built yet, but the path is open. Either way, the front end is where you and us meet, and that's the best for the next round of our work. Okay, let me close. Here's what's coming next. Three things. First, we are going to open source George, and the library is going public. Two, we are working on proof generation for full ZK VMs using George and SPN hypercube workloads on top of our compiler. Last, formal verification integration. And honestly, this is the part I most want to talk about with you after this talk. And yeah, that's the ask. And if any of this overlaps with what your group's doing, I'd love to talk after. And one last thing on a title, provably fast, it works two ways. Fast code that can be proven is what we have been building, and it is really proven by measurements that the code is really fast. So yeah, but meaning live in the same place, the compiler. And I think, yeah, in conclusion, I think we need a GK domains compiler, not just for performance, I think, but for formal verification too. The performance comes along with it, and the verification is where we need your help. And that's it. Thank you for listening to my presentation.
Thank you very much. Any questions from anyone? We have a bit of time.
I have just one idea about how to integrate this with formal verification. So at the end, I want a theorem about the PTX code, like this PTX code does growth 16 what. And then one way to get at this, I mean, you have done a lot and this helps a lot. So like, when you compile something, you can record the lowering steps and optimization steps in a text file with some explanation why this is supposed to be correct. And then you give this text file and the resulting PTX code and the source code to a language model and ask the language model to write a lean theorem about the PTX code, why this does the source, what that source does. And, since the compiler has printed all the explanations of the, intermediate steps, just, some very, very, a few sentences is enough for each step. Like, then, I mean, I think today's language models are clever enough to like figure out the details to write a theorem about the PTX code. And when you do that, you do that for like 10 times, 20 times, and then you can ask it to write a compiler in Lean with theorems that with a theorem saying that this preserves the meaning of the source to the PTX. So there are things you can do already. These are just ideas, like just speculations might work. I think it's, there's, I see a good chance it kind of works, but yeah, it just what came to my mind.
So in conclusion, you're asking is like, so you briefly try to generate a proof between the layers, because we have a lot of layers connecting to from the high level to the low level, go down to the PTX code generation, and you're going to ask language model to produce a lean proof that every direction is the going right, is something.
Yeah, everything going. So that is the that's the ingredient. Every step is going doing some some sound things. But the goal is like the PTX code does what the source is trying to say.
Yeah, I think
source looks Python, and the language model needs to like guess what the Python code is saying and translate that into some lean function or something. But these things are kind of good at like writing lean code based on Python. And at the end, you have to like look at some auditor needs to look at the lean theorem, and the auditor needs to read the lean theorem at the end, but the statement can be as short as the Python source.
Yes. Yeah, the main point of this talk is like, yeah, you can fix the source language as Python level, which is fixed across the, like, for example, like over time, for example, no matter what there's a new hardware comes in, no matter what there's a new algorithm comes in, you can fix the source language. This is the kind of ledger. And then, yeah, if you generate, if you can, yeah, as you talk, if you can generate, prove that the steps lowering down to the in the end is proven to be correct, then yeah, I think it really sounds cool, and I think it's the end game for me.
Yeah, I guess the end game is like, I mean, just right, having the compiler in Lean, that's kind of proven to do the right thing. That will be the end game. What I described is a couple of steps before the end game. That's it from me.
Yeah, it sounds makes sense.
Yeah, go ahead, Bess. You're muted, Bess.
Oh.
I think it might be. I can see the like mute and unmute show up on Google Meet, so it might be a microphone issue. But I can read out obviously Baz's comment from the chat, and we'll see if you can add to it with your debugged microphone. So Baz was saying, obviously, so Baz, for context, have been doing a lot of very cool work, porting obviously things from Rock to Lean and doing verified compilation in Lean and connecting a lot of things in Lean. And so in particular, he's got a verified compiler for cryptography in Lean from Hacks that can go down to CPU backends, specifically x86, ARM, and RISC-V. And there's some integration between this and Jasmine. I guess, Baz, maybe you have your phone on, I guess, now?
Yeah.
Yeah, we can hear you now, so I'll let you take over.
Yeah, thanks for reading it. Yeah, really cool work. I had a quick peek at your work when Alex announced your talk, and I think I fully agree that this is the way to do it. So I had been coming from some similar ideas from another direction. So I had also been working on MLIR and connecting it to the compoly work already, because there's one of the dialects that actually fits very neatly on top of that. There's already an MLIR framework or two MLIR frameworks in Lean, so that's actually very nice to build on that. And so what I've done is to port the work that I've had for elliptic curves and also general the work on Jasmine. So all of that is in Lean already. So I actually have the verified compiler for the parts that you're looking for, going to CPUs, but not to GPUs. And so it's only the sort of the middle end you need. So basically going from your prime IR to CPUs. But it would be, I mean, very interesting to connect that to GPUs too, and also to connect your front end to the middle end. So I started from Rust, from Hex, and so what I've done, it's, I mean, as you say, it can be made competitive or even faster than production code. That's also my experience, and that can not only be done in MLIR, but also from Lean. I mean, the compiler is in Lean, but you're running on hardware, of course. So I think we should have a chat with the group of Tobias and also the people on Arclip and Compoly to integrate all of this and make sure that we standardize all these intermediate languages. Probably also talk to the CSLib people.
Yeah, sounds like I'm open to collaborate with all of you guys. So yeah, please have a chat after this talk, and yeah, let's continue talk. It's okay.
Yeah, but very nice work.
Thank you.
Yep. Yeah, so on that note, so there'll be around end of August, September, Tobias is doing an event related to kind of Lean and MLIR and all of this. And so maybe that can be a place to all meet up and chat about this. But I think, yeah, broadly speaking, I think there's a clear path that's starting to emerge as to how to all this, which is very nice. Do we have any other questions? Otherwise, I have one as well I wanted to ask. All right, then I'll ask mine. So one question I've had for a while is, so with reference actually to this kind of MLIR and Lean work, one question has been how to add support for GPU backends in Lean. So in particular, right now, there are semantics for things like RISC-V. You could extract to the cell x86 semantics to Lean and so on and so forth. We don't currently have semantics for any kind of GPU targets in Lean. Now, one candidate target is TileIR, which is a relatively new IR developed by NVIDIA. And the reason for this being a good target is that this is already an MLIR dialect. And so adding support for this in Bear is somewhat straightforward. But obviously the PTX is, you know, the, let's say, canonical low-level IR. I guess, are there opinions on, you know, the GPU engineering / you know, kind of GPU performance side of things on what, you know, the right targets are in terms of balancing the ease of integrating this with Lean in terms of obtaining semantics or, you know, some MLIR format for these, with obviously, you know, how much benefit you get from working with different IRs. And so obviously, I mean, you obviously like stable HLO in your current stack, and you go to PTX fairly straightforwardly. But that, I think, is an interesting question of, what are the right GPU backend targets to get semantics for and verify.
Actually, I am a very new to in this domain, so I never have a long time to think about it. So I need to take time to think about it. To be honest, I rarely know about the MLIR. This is the first time to hear about it.
The MLIR is very new.
Oh yes, so
I'll put a link in the chat for
okay.
people
So yes,
who want to have a look at it. It may be the first time for several people hearing about it. But yeah, the main appeal of MLIR is that it's already an MLIR dialect, and so porting it over to Lean is somewhat straightforward because there's already basically MLIR in Lean. But it's like some late 2025, 2026 style of thing.
Yeah, because from my side, like the number one priority is performance, and the make the Python like stable level, the George or JAX or whatever. In that sense, like we want to reuse the existing machine learning the works as much as possible. In that sense, if the MLIR is not ready to be productized from the machine learning domain, and it requires to put a lot of work on our team, and that's why, yeah, I think maybe if it's good for verification purpose, then I think it could be the one thing we can put together and figure out how it balance between performance and verifiability. That's one option, I think.
So I think that discussion will kind of keep going. But that was a topic of discussion with I know we had this discussion with people who are working on Hair and FHE compilers as well, and the conclusion of the discussion we had was that we really couldn't decide which GPU backend would be kind of highest priority to verify based on the different trade-offs. And so it's, I think, somewhere where the opinion of GPU engineers is very important to make the right choices as well, beyond ease of verification.
So I'm born as an engineer, so for me, like if I can reuse the existing work, then I try to reuse the existing work. That's the fastest way to get to our destination.
Okay, then we'll keep that conversation going then. Okay. And I guess I don't know if you still have your hand up, Basil, if it's just from the previous question.
Two remarks. So can we have the discussion on Lean Zulip? And
yes.
I don't know whether you're there. The other one is that Lean MLIR is in flux at the moment, so they're moving to this verified AR. So I'm hoping we can solve that.
Yes. I mean, Ver is completely deprecating Lean MLIR, and so it's easy to just look at Ver and ignore Lean MLIR for now. Most of the work is still going on in the main Lean MLIR repository is clean up for some projects that we're finishing that needs papers and whatnot. So when I say Lean MLIR, I mean Ver now. Actually, it's a bit of an abuse of language, which is unfortunate. But fantastic. Then we're right on time. So if there are no other questions, we can leave it here for now. I'll post a couple links, I guess, about Ver and things like this in the chat on Telegram, and Ryan, I'll get you on the Lean Zulip as well. So all of this can be discussed with Tobias and some of the other Ver people, and we'll keep the discussion going. Okay, I'll stop the recording, and thanks everyone for coming. Thank you very much for the attention, Ryan, and thanks also Yuichi and Baz for the great questions.